Well, sometimes, even if there is a GCF, you still have an A value, a leading coefficient that's greater than 1. So we better review that. So always look for a GCF, though. That's your first step. So like in 56, the numerator, we can factor an n out. So we're left with 2n squared minus 11n minus 90. And on the bottom, we can factor out a 3. All right. So on the bottom, and maybe you're getting used to this, folks, you're kind of just seeing how to factor when a equals 1. Because on the bottom, a does equal 1, so we'd have just a plain n in front of each of the binomials, or at the start of each of the binomials, and we'd have n minus 10, n plus 1. But on top, oh, we can't use that quick factoring method. We have to use the AC method. It's going to be kind of similar, but you need to take, oh, geez. You need to take your A and your C and multiply them together. Oh, no, I'm afraid of how big of numbers. I thought I tried to cut these numbers down. You got to multiply your A times C. You're looking for numbers that multiply to 180 and add to negative 11. Really, when we do this, when A equals 1, you could, I don't know, you could still think of multiplying A times C together, but we don't have to just split the middle anymore, which is nice. Anywho, I'm just kind of stalling while I think of the right combination that multiplies to this. 30. Oh boy. So, ten times 18. It's going to be a bigger gap than that. Oh, 9 and 20. 9 and 20. Make 20 negative. Still, hopefully, I think they usually use a little bit smaller numbers. Apologize about that. Oops. N minus. Oh. This is not the A equals 1 method. We're not done. It's not that easy, folks. It's not that easy. So we need to rewrite this trinomial. 2n squared minus 11n minus 90. Well, when we get these numbers, shove n's behind them. Because this negative 11n, we have just turned into 9n plus negative 20n. Yeah, folks, like when you think you factored something correctly, multiply it together, make sure it truly equals what you equated. If I plugged those back into the parentheses, that would not have been equal to this polynomial right there. We have to do this method here. So now you do factor by grouping. You can take an n out of each of these terms. And in the back, you can take a negative 2 out of each of those terms. Negative 20, negative 10, negative 10 out of each of those terms. Notice when you factor out a negative 10, you're left with a positive 2n and a positive 9. See how these binomials match? That's good. And then you put your GCFs together. So we had n and negative 10. I'm sorry that was written so sloppily. And then 2n plus 9. This is what goes back up there. N minus 10, 2n plus 9. So these factors are the same. And now we have our final answer of n times the quantity 2n plus 9 divided by 3 times the quantity n plus 1. There we are. Bada bing, bada boom. Number 60, I can factor a 2 and a p out of the top, which leaves me with 5p squared plus 9p plus 4. Let's double check that I did that really quick. Multiply that back in mentally or physically. Does that work? Is that right? Yes. On the bottom, we can factor out a 9. So, got got to try to factor this even further and this even further if we can, folks, and they are both likely factorable. On the top, multiply your A and your C. You get 20. So we're really looking for ways to multiply to 20 and add to 9. That'd be 4 and 5. But put p's after it. So we rewrite this as 5p squared plus, not 9p, but 4p plus 5p plus 4. And so we can factor out a p from the first one. And we can't factor anything out of the second one. If you don't like that, folks, if this is, sometimes people don't, they get stuck on factoring that one out. Realize that you can always take that 4p and 5p. You can switch them around in that blue area. Then you'd be able to factor a 5 out and a 4 out. In the end, when you regroup, you will get the same answer. Although your factors might be switched. You might have 5p plus 4 times p plus 1 versus this p plus 1 times 5p plus 4, but multiplication is commutative, so it doesn't matter. It's fine. It's the same. It's equivalent. Now, on the bottom, you might be saying, I don't think I can factor that. Well, if you want to do a diamond, we're looking for ways to multiply to -1. And notice, this is the same as p squared plus 0p minus 1. We're looking for ways to multiply to -1 and add to +1. That's 1 and -1. P plus 1, p minus 1. Yeah, Lucy? So, we have a final answer of 2p times 5p plus 4. There we are. I'll do one more down here. I'm going to do 62 because I think that difference of squares, that pattern that you just saw when we only had 2 terms, which shows up on 62 on the bottom, is good for us to see. You know what's nice about this one? With practice, you see how if these are going to be easy or tough or not, folks. This top one, oh, I treated you. Oh, you got away with one. That's a GCF, so now our A values, oops. Our A value is 1, which is good actually, because sometimes people just get in the habit of always having to do the AC method once we start doing that. So 3, and then numbers that multiply to 4 and add to 5. That's 1 and 4, so x plus 1, x plus 1 times x plus 4. On the bottom, this is difference of squares. Numbers that multiply to -1 and add to 0. So it's like x plus 1, x minus 1. And yes, folks, notice these factors right here are the same. Lately in the examples that I've been doing, they've been right on top of each other. Like the first factor and the first factor, the second factor and the second factor. We can rearrange multiplication like I mentioned earlier. So like it doesn't matter that this is the first factor on the bottom and that's the second factor on the top. We can rearrange it so they're on top of each other, but they don't need to be that way. They're common factors on the top and the bottom, so there we are. So our final answer is this.